no matter where you are. Welcome to the Geo Earth webinar. Actually, Yunfeng should host this. Yeah, anyway, I'm going to replace him to introduce Mingming. Mingming got his undergraduate degree in Yunnan University, and then his master's in the Chinese Chemical Sciences at the Institute of Geology and Physics, when he was doing the seismic tomography. Then he moved to Arizona State University and began Ford Morgan work for his PhD, and then at the CU Boulder in Colorado for his postdoc, continuing a geodynamic process before he moved to his current position at Arizona State University, I think 4 years ago. So today he's talking about the new progress that on the topic that he's very familiar with, has been keeping on in the recent, I would say, for 1 decade already on the large low shear velocity provinces. So with that, I'll give the rest of the Mingming.
Okay, thanks for inviting Zhang Zhao, and thanks for coming and to my presentation, everyone, and good morning. And today I'm going to present one of our most recent research about the deep mantle structure and dynamics. Okay, so how can I go to? So although today I'm going to talk about mantle heterogeneity, I will focus on mantle heterogeneity, but to the first order, don't forget that the Earth is layered, like more than 90% of it is layered. Okay, so the anomaly is just very small anomaly, usually within 10% variation of seismic velocity, density anomaly. So we're just going to focus on these small anomalies. Okay, so as you can see, they are like small perturbations of physical properties. But this is just this small perturbation that makes things very interesting and makes Earth convecting and makes lots of things happen. Otherwise, the Earth is going to be dead. No, it's kind of boring. Okay, so this slide, you don't need to remember anything. I just want to show you is seismic tomography models from shallow surface at 100 kilometers to near the common boundary. Okay, so in seismic tomography, actually in all seismic observations, red color means low velocity, blue color means high velocity. And sometimes I present horizontal cross sections, like at each depth, global at each depth. And sometimes I plot these vertical slides or vertical cross sections. Okay, and my research is focusing on understanding what causes these seismic heterogeneities and how do they evolve with time. And this is important because seismic observations only provide a present-day snapshot of the present day, but the question is what causes this and how do they evolve with time? And we use the tool of geodynamic modeling. Okay, so the concept of geodynamic modeling is pretty simple. It just we think the deep physics processes are controlled by fundamental physical laws, very fundamental, like conservation of mass, conservation of momentum, conservation of energy. They are like just conservation equations, like conservation of mass makes sense, just material does not disappear by itself, does not create by itself. Conservation of momentum is basically force balance. So there are multiple forces. P is pressure force, eta is viscous, okay, eta times epsilon is viscous force, and on the right side is buoyancy. So basically it's a force balance, like F equals to ma, like very simple. Conservation of energy is like energy is conserved. Okay, so energy heat advected to some place, then it's going to increase the temperature. Heat advected out of some object is going to reduce the temperature of the object. So these are fundamental physical laws, and these laws basically applies to almost all objects, like including Earth's mantle as well. So, but the problem is that these equations, although they look really simple, but like if you consider two-dimension, multi-dimension, all of these variables, they depending on both time and space. Okay, and it's very difficult and almost impossible to solve these equations by hand. And we use computers to solve these equations. And specifically, we use finite element method. Okay, and so that is a brief introduction of what I do as a geodynamist. Okay, and next I'm going to talk about one of my recent research. The title is Unstable Structure and Dynamics in Earth's Deepest Mantle, which is a low-most mantle. Okay, and Chen Yuan is my current student, and most of this work, the geodynamic modeling experiments, have been done by him. And he just graduated, and he's going to be doing his postdoc in Caltech starting from August. So maybe some of you know him, but so like in this slide, I show the global seismic shear wave tomography model. And again, red color means low seismic velocity, blue color means high seismic velocity. The most important structure in the low mantle is these large low velocity provinces, so LLVPs. Okay, and some people call them LSVPs, but we decide to call them as LLVP because even the P wave velocity is also reduced. So, and throughout the presentation today, I'm going to call them LLVP, but sometimes I may call them LSVP. I get used to call them as LSVP. Okay, and as you can see, there are two LSVPs. There, one beneath Pacific, and the other is beneath Africa, and they are very big structures and extending from the core mantle boundary to quite some distance, like thousands of kilometers away from the core mantle boundary. And so this is just a 3D view of the tomography model, the same tomography model, or actually different tomography model from a different group, like from Berkeley group. And again, red means the LSVPs, okay, one beneath Pacific and one beneath Africa. So this is, and there are lots of tomography models. Like depending on what data you use, what method you use, it is from different types of groups. Although the small scale structure variations of this small scale structure, they differ model by model, and actually in all the model there are two LSVPs. So it's very, very robust feature, like there are two large low shear velocity provinces in Earth's low-most mantle. Okay. So like this is just some cross sections of the tomography model, and like it looks really complex. Okay, like some different cross sections shows different morphology, and one of the questions we ask ourselves is what controls this morphology of these two LSVPs, and because LSVPs, they are shaped by mantle convection. So we think that by understanding the shape, understanding the morphology of the LSVPs, we can learn a lot from the nature of mantle convection, like also from the physical properties of the deepest mantle. So, and the first question we want to ask is, what is the maximum height that can LSVP reach? So as you can see from these cross sections, looks really complex. It's not easy to figure out what is the maximum height. Okay, and to do that, we also try lots of methods, and eventually we found one method, simple method, which works very well. And in this slide, I'm going to show you what's the method that we use. It's very simple. And here is just one example. Is actually a cartoon in this left figure. The red means there is LSVP. As you can see, usually the LSVP is wider at the bottom and narrow at the top. Okay, and on the right figure, the horizontal axis means the horizontal average velocity, and the vertical axis is distance from the CMB. So like, for example, if I draw a horizontal line here and I calculate average seismic velocity at these steps, then I'm going to get one value. Okay, like let's say this is a dot, this is one value, and is at this distance away from the CMB, away from the common boundary, and the horizontal average is this point. There is no numbers. Don't worry about the number. It's just a concept model. Okay, just cartoon model. And then I calculate the average seismic velocity at least the shallower depths. Then, as you can see, it becomes narrow. The LSV becomes narrow, and there are more blue region, but less red region, and you're going to expect the seismic velocity, the average seismic velocity is going to increase, okay? And if you go move up away from the CMB, you are going to just get different velocity of this, okay? So like for this one, it just there's no more LLVPs anymore. As you can see, you are going to get kind of this trend, and we do curve fitting to this trend, and then we define this point which the curve start to turn. We call this as turning point, okay? And you can also actually calculate the gradient of this, and the gradient will be very different at this point than the other points, okay? And we define this point as the maximum height of the LLVP. So this approach is very simple, but it also allows us to process lots of cross sections, lots of seismic tomography models. We don't need to worry. We even don't need to worry about how do you define LLVP regions. We just do this like naive calculation, very simple, and we apply this method to the seismic tomography models. We tested all the available seismic tomography models. There are about 17 of them, and this is one of the example. The yellow color shows the regions of the LLVP regions from the SRT, like RTS40S, like from Eurasimus model, and we draw lots of cross sections, cut through the Pacific LLVP, cut through the African LLVP, and we calculate. These are all vertical cross sections, and we calculate the horizontal average velocity as function of depth, okay? And there are 4 figures here. So the 2 figures on the left part shows the results for the Pacific LLVP cross sections cut through the Pacific LLVP. So, and the right figure, the 2 right figures on the right, the 2 figures on the right shows the results of the cross sections that cuts through the African LLVP. As you can see, this is kind of complex, but so what we found that if you do calculate the average of these different tomography models, and you are going to get this very thick blue dashed black curves here. So as you can see, the turning point for the Pacific LLVP is here, which is about 800 kilometers above the CMB. However, if you look at the African LLVP, the turning point is about here, about 1700 kilometers above CMB. And this, the difference between the top 2 figure and the bottom 2 figure is, the major difference is that on the top one, we calculate average velocity in all regions, but in the bottom 2 figure, we only calculate average velocity where the velocity is only negative. Okay, and this is because we think the LLVP regions should have low seismic velocity, like negative seismic velocity. This is even more obvious from the low 2 figures, like turning point for the Pacific one is about here, about 700 to 800, and the African one is about here, about 1700 to 1800. Okay, and we found these 4 cross sections that shows the maximum height of the LLVP. So first of all, I want to say that I keep using the word of maximum height, and this is because the LLVP are complex. It will have different height at different places. Okay, and we are focusing on the maximum height that the LLVP can reach. And these 4 cross sections show the locations of that we find the height is the maximum. Okay, and the result is showing here, like cross section A, cross section B are for Pacific one, and you can see the top of the LLVP is about here, 700, about 700. kilometers above the CMB. And the African one, the maximum height is about here. As it's really clear the turning point. And that is about 1,700 to 1,800 kilometers. So that means the African LLVP reaches a height of 1,700 kilometers above the CMB. And this is about 1,000 kilometers taller than the Pacific one. This is very, very interesting. And this is 1,000 kilometers is very long distance. It is a really big deal. Okay. So then the question is, actually, what causes LLVPs? And then the next question is, what causes the vastly different height of the two LLVPs? So to answer the first question, what causes LLVPs? There have been lots of ideas about LLVP, and one of the most popular is that LLVPs are caused by thermochemical piles. Thermochemical piles are these structures, and they have different composition, and these composition are also different, has different density, is intrinsically denser or compositionally denser than the background mantle. They also, at the same time, they are also hotter than the background mantle. Okay, and this is one of the most popular hypotheses. Right now, there are also other hypotheses like plume cluster, purely plume, super plumes, and we are going to just assume the LLVPs are caused thermochemical piles in this presentation. And this figure shows results from previous geodynamic modeling. Can you hear me?
Yes, I can hear you. I turn your video off because I think.
Great. I disappeared just in case I still.
Yeah, it's okay. Is your screen on the Gennaro and the McNamara 2008 paper?
Right. Yes.
Okay, go ahead.
Okay, great. So this figure is from geodynamic modeling, and the brown color represents thermochemical piles. Okay, and as you can see, the thermochemical piles and the surrounding the piles, they are just called dome wallings. Basically, the thermochemical pile material, they are just pushed around by subducted slabs. Okay. So, and then if we assume the LLVPs are caused by thermochemical piles, then we can change our question to this, and what causes the height of the thermochemical piles. Okay, so instead of trying to answer what causes height of LLVPs, I modify the question of what causes height of thermochemical piles, because I assume the LLVPs are caused by thermochemical piles. And if we make this assumption, and then we can do numerical model experiments to understand what causes thermochemical piles. So in this slide, the left one shows the temperature field, initial temperature field, like it's all white color right now, and white color means the temperature equals to 0.5. It's non-dimensional temperature, like 0 means you can show like 0 means 0 degree surface temperature, 1 means the maximum temperature, maybe like the CMB temperature, and 0.5 is something in between. Okay, and the right panel shows the compositional field. The black color means background mantle material, and the yellow color means the thermochemical pile material. And the color bar shows the effective buoyancy ratio. So you can think about this effective buoyancy ratio as the compositional density. Okay, so basically the yellow material, they are a few percent denser than the black material. So this is our initial condition from surface to the CMB. So let's run the calculation. Very simple, like 1x1 box 2D Cartesian model. Like all boundaries are free slip. Okay. So as you can see, the thermochemical pile materials, they just push to the other side by subduction. Okay, on the right, on the left part, there's called dome walling by represented by these blue color regions, the subducted slabs. And here shows the location of the thermochemical pile. It is hot, as you can see, the temperature is pretty high because it's close to the core, and also because the temperature is very difficult to get advected out to the background mantle, and it's also conventionally dense. So, and because it's hot, then if you increase the temperature, it's going to reduce the density. However, because these materials are already quite dense, like conventionally really dense, and if you consider the thermal and the chemical effects on its density, so then you are going to find this thermochemical pi is about neutrally buoyant, like the density anomaly is about 0. Okay, so let's go to the next slide. We did lots of calculations, like similar calculation, and this slide just show different models there, and from ABC, like from A to B, in figure we increase the volume of the pi material, as you can see in the figure D, figure E, figure F, and you can see from left to right, the volume of the red color of the volume of the thermochemical pi material, they increase. Okay, however, it's very surprising, like although the volume increases, the height does not increase. Okay, and the only change is just it becomes wider and wider, but the height does not change. So basically, we found that the volume does not affect the maximum height. And then in this this is another stream model. From left to right, we increase the background mantle viscosity, so from lower to high. Okay, as you can see, as we increase the background mantle viscosity, the thermochemical pi, the maximum height becomes larger and larger. Okay, but not that much, slightly larger from left to right. Okay, so that means the background mantle viscosity, they also affects the maximum height of the LLVPs. Okay, so like usually pies are taller when the background mantle is more viscous. And it's the most important parameter is the intrinsic density of the pi material. Like from left to right, 3 figures, we increase the density of the thermochemical pi. It makes very perfect sense, because if you increase density of some materials, it becomes very difficult to push them up to really high topography, right? So, and there's no surprising, as you increase the increased density of the pi, it becomes the height becomes much reduced, much smaller. Okay, so the density work conclusion is that the density of the pi material is the most important. Like piles with larger intrinsic density, they have much lower height. Okay, and this figure just shows how the height of thermochemical piles are controlled by each different parameters. In figure A, we show the height in vertical axis, horizontal axis is volume of the thermochemical pi. It's actually volume percentage of the thermochemical pi, because we treat the area of the entire model as 1, and then like 0.1 means the pi occupies 10% of the model area, model domain. And as you can see, it's almost the height is not very sensitive to the volume percentage of the pi. Okay, and we in figure B, we increase the density, which is represented by buoyancy number. You can see as you increase the density, the height of the pi becomes lower and lower. Okay, and in figure C, we increase the background mantle viscosity. As you increase background mantle viscosity, the height of pi also increases quite significantly from this figure. Okay, and in figure D, we also test calculations. We change the viscosity of the thermochemical piles. It has some effects, and particularly if the pi viscosity is much larger than the background mantle viscosity. However, the effect is quite limited. There's almost just about 200 kilometers variation. Okay, and there's no way for this, and for figure A volume and for figure D pi viscosity to explain the 1,000 kilometers difference of pi height for the two LLVPs. So the only solution is buoyancy number and the viscosity of background mantle. Okay, And you may think these are just too simple 2D model, Cartesian 2D model, but actually we did lots of other tests. We increased the size of the model domain, and we did different viscosity laws, temperature dependent viscosity, different types of different activation energy. We also performed 3D models, and in regional 3D in spherical geometry, and all of these calculations support our conclusion. Okay, they are all more or less very consistent to each other. And this slide summarizes all the results from all the models. So it is a little bit complex. Okay. So first of all, let me try to explain what's the meaning of these colors. The horizontal axis is a background mantle viscosity, okay? There are lots of background mantle viscosity, and like each box in horizontal direction represents different background mantle viscosity, and vertical axis shows the buoyancy number. And the buoyancy number, you can translate buoyancy number to density anomaly, which are shown in the right vertical right axis. Okay, there are lots of small cells or small boxes here. So each box represents one calculation, one geodynamic model, and the parameter for each box is given by the buoyancy number in the vertical axis, and by the background mantle viscosity in the horizontal axis. Okay, and the color represents the maximum height of thermochemical piles in this model. Like for example, I'm not sure if you can see my mouse or the arrow here. Like for example, I'm pointing to a box with blue color, and you can go to, so this blue color has buoyancy number about 1.0, and about mantle viscosity about 1.2 times 10 to 23. Okay, and it's a little bit blue, so that means in this model, the height of the thermochemical pile is about 700 kilometer steps. Okay. And then, as we said before, the height of the Pacific LLVP is about 700 to 800. That means it's from 700 to 800. If you look at this color bar, it's about blue color. Okay, so then we map these stars, these pink stars on locations where the height is 700 to 800 kilometer steps. And in contrast with the triangles, the cyan triangles represent the height of the African LLVP from 1500 to 1700. Okay, and the triangles represent triangles here. And there are also other calculations represented by these gray crosses. And these calculations, for these calculations, the buoyancy number is so low, or the density of the pie is so low that the pie is actually not really stable. They just get mixed or lost very quickly in the calculation. And as you can see, the height of the Pacific LLVP can be explained by a very big range of parameters, including buoyancy number, very big range of background mantle viscosity. However, to be consistent with the height of the African LLVP, we need to make the buoyancy number pretty low, like about 0. less or equal to less 0.5 or about 1% intrinsically denser. Okay, and if you just further reduce the viscosity by a little bit, the pie is just going to be very unstable, just going to be entrained away. Okay. So the take-home message is that the height of the Pacific LLVP can be explained by a wide range of parameters. However, to explain the large height of the African LLVP requires it to have a relatively low intrinsic density. And because the African LLVP is relatively have low intrinsic density, and we think it may be very unstable. So that means then the next question we try to ask is, what will happen if a thermochemical pile is not dense enough? So we found that in this case, so if a thermochemical pile is not dense enough, its height will be greatly affected by the surrounding mantle flow as well. And this is another calculation that we performed, which is not included. We kind of follow up study from of our just recent published paper published in Nature Geoscience. And the top panel shows temperature field, the low panel shows the compositional field. As you can see, like again here, they are the like dark color represents thermochemical pile regions. And let's run the model. Just pretty short model. As you can see, right now at the bottom, there are multiple thermochemical piles. Actually, 1, 2, 3 big thermochemical piles. There are some small ones, but very small ones or too small to be comparable to the LLVP. And in this calculation, and the thermochemical pile, all the 3 thermochemical piles, they have the same density. The density of all of these 3 thermochemical piles, they are all pretty low. Okay. And you can see that this pile reaches much taller height than the other 2 pile. And if you watch the movie again and again, you are going to find what's the reason which this pile reaches much shallow height. And the reason is basically that this pile has been pushed up by the subduction from both sides. Okay, so you can watch this again. And it has been pushed up like this, big subduction pushed on to the left, and here is another subduction pushed to the right, and it's kind of squeezed to the center region. Okay, and it becomes really large height. And this study is currently under review. So, and we think another possibility is to explain the very big height is just the 2 LLVPs. They may both be not very dense, both be very unstable, but it's just African LLVP, they have been pushed up recently by subduction, but the Pacific LLVP is less pushed up by subduction. And you know, like for the Pacific LLVP, there are lots of stagnations. Most of the subduction slabs, they are stagnant or near the bottom of the mantle transition zone. Okay, so that may be the reason why the LLVPs why the Pacific LLVP has not been pushed up by subduction until right now. Okay, so the take-home message is the sinking of subduction slabs to the deepest mantle pushes a pile nearby to have large height. And there are very good implications. So our result basically implies that under the Pacific, actually the African LLVP, they have been affected much more strongly by surrounding convergent flows. Okay, and if you simulate the background mantle flow field, I'm sure that you are going to find that somehow the African LLVP surrounding the African LLVP, the mantle flow field is much larger than the mantle flow field surrounding the Pacific LLVP, and this can be consistent with our explanation. Okay, so let's go back to the question, what causes the vastly different height of the 2 LLVPs? So one reason is that the African LLVP is less dense than the Pacific LLVP. So this is very obvious, okay? Like the usually light materials, they can rise, dense material, they rise less. And another explanation is both LLVPs are not very dense, but the African LLVP has been pushed more strongly by surrounding convergent flow. So if this reason B makes more sense, and in my opinion, it does make more sense. Okay, although reason A is we cannot exclude the possibility of reason A, and reason B, in my opinion, personal opinion, makes more sense. So like if answer B is correct, the African LLVP should have been rising in most recent geologic time. So if you have very broad implication if the African LLVP has been rising, and it may affect the surface topography, causes like loss of volcanism, and it is consistent with observation, right? Like there is Eastern African rift, which has been broken, maybe because of the rising of the African LLVP, and the dynamic topography of the African continent is also get increased in the past 100 million years. Okay. So to really tell which region makes more sense, more realist, we really need to understand what are the physical properties of LLVPs, particularly the density of the two LLVPs. So is the African LLVP less dense than the Pacific LLVP? That's very interesting question, and also very important question. And also, what is the nature of amount of flow field? The amount of flow surrounding the African LLVP stronger than the amount of flow surrounding the Pacific LLVP? This is another question. And to constrain, actually, to answer these two questions, we need seismologies, we need physics experiments too, and we basically need a lot of collaboration, interdisciplinary collaboration, and how does the surface respond to the rising LLVP? Like it will affect plane motion, affect surface topography, affect gravity, volcanism. It may also like indirectly affect the location occurrence of earthquakes. Okay, and I think that is pretty much for my presentation, and I'm happy to answer any questions and also be criticized. Okay, and thanks for listening.
Thank you, Mimi, for the presentation. Now is the time question from our participants. So feel free to type your question in the chat, or you could just open your mic and ask a question directly.
Hi, Zhang Zhou.
Yeah, Yang-Ting, please go ahead from
Ming, this Ting. So
yes,
can you hear me?
Yes, Yang-Ting, nice to see you.
Okay. Let me. So if the LLVP has a so small density, so does that mean that LLVP cannot be long in the history, or it can only be formed during the recent history of the Earth?
Oh, so the question is, if the LLVP are not stable, that it mean there are more resonant structures, or actually, I think that's possible. They may be resonant structure, relatively resonant structures. However, they can also be very old structures, because the density of the LLVP thermochemical piles, they are going to reduce as function of time. As long as you entrain more and more less dense material within it, its density is going to be reduced as function of time. And it's very likely that we are just in a very special time right now. And in this time, the LLVP just becomes unstable and they are going to disappear. And I usually think, and this kind of special time, we are in a very special time, like and in this time we have human beings, right? We are in a very special time. So, and there's no reason to say that this is not going to happen. So like so overall, like in short, and I do think the LLVPs, they are unstable, and they may be stable in the past, but at least they are not stable right now. Okay.
Okay. So in this case, we are very lucky. The LLVP was very stable in the 4 billion years, but it's unstable till now. So the second question is that, you know, that the African LLVP is beneath the Pangea, the supercontinent. In this case, because it is beneath the stable supercontinent, does that mean the downwelling flow beneath the surrounding the African LLVP will be, I guess it would be smaller than that surrounding the Pacific seal plume or LLVP. Yeah.
Not really. The downwellings, they never occur in supercontinents. They occur in surrounding the supercontinents. And one of the largest big downwelling that affects the African LLVP is the Asian Tertius subductic slabs. And this Tertius subduction of the Tertius slab, Tertius oceanic plate, is very, very important. And it actually, because of this subduction, the Indian continent, they move very fast and hit the Tibet and Caucasus Tibet, okay? And this subduction may at the same time also causes the African LLVP to rise as well.
Okay, thank you. Very nice talk, and thank you for your talk. Thank you for your presentation. Okay.
Okay, so next question is from AA. He's listening in the chat. I'm going to read the first question. Is what are the compositions that you use in your simulation for the LLVPs, since they are chemically different?
So we did not specify the composition in our models. What we specify is the density structure of this material. However, many different compositions can be intrinsically denser than the background mantle. More of a basalt subductiogenic crust can be more dense than background mantle material. Asian primordial material can be denser than the background mantle material. There are some other materials. Physics has been proposed lots of compositions for the LLVPs, but there are lots of possibilities that can make the thermochemical pi dense. But in our experiments, we did not specify what composition. We just say, okay, as long as you have this density, it's going to look like this. Okay, have this topography. So maybe I missed the point. How do you define average?
So the question they were asking you to explain that. So how do you define the average horizontal velocity?
Is here. The average horizontal velocity is just at each depth we calculate the summation of all the velocities at every location, and we use the summation divided by the number of samples to calculate the average. So with the average is at each depth stays average, okay. And as a result, we can show a curve here, and this makes more it's clearer. Horizontal axis is average, and the vertical axis is height. Okay, at each depth there is a value, and you form a curve like here.
Is that velocity only calculated in the yellow region or the red region, or also in the white region?
It can mostly in the yellow region, but we also extend a little bit outside into the background, into the white region.
Oh, thank you.
Yeah.
Okay, so next question, please.
Okay, I have a question. First of all, it's a very impressive talking about the LLVPs. My question is about because I see you propose that the push by the convective mantle or
yes.
the ambient mantle
yes.
to the LLVPs, very important factors for the upwelling of the or higher height of the African LLVP. But I'm just concerned, or what is the force or the what controls the mantle convections in the lower mantle to push the
the question is what causes the convection?
What kind of force can push? Is it a subduction of the plate?
Yeah. Yes, subduction. So basically, convection is due to density anomaly. Okay, if you have large density anomaly, it's going to like move faster, causes larger force, and the subduction is very big. Okay, subduction slabs very big, very cold, also very dense, and like maybe the major driver of mantle convection is subduction. Like, although I keep saying the two LLVPs, they are very big, but if you calculate the volume, it's only about a few percent mantle volume. Okay, and the background mantle is much larger than the two LLVPs. So that means the LLVPs control a very small amount to the mantle flow field. The mantle flow field is mainly driven by subduction. Okay.
Okay. Another question is now, because I see your result is the height of the LLVP is similarly positive to the viscosity of the lower mantle. For me at first glance it seems opposite to the common sense, because not common sense is because in imagination it is when the mantle is more soft or something like that, it is more easier to upwelling. Because your result is it looks like the lower mantle is it is a C, the picture.
Oh, figure C. Okay.
Viscosity of the background mantle, it is more stiff. It is more easier to upwell.
No, not really. It's kind of counterintuitive. Like, if you increase background mantle viscosity, it becomes if you calculate the stress, it's going to increase a lot. We calculate the stress, and we found that as you increase the background mantle viscosity, the stress surrounding the thermochemical piles, they just increase, because stress is calculated by multiplying viscosity by the velocity gradient of velocity. Okay, and background, and there are two effects, and in our calculation, in our model, the background mantle viscosity it wins. So like, you can think about, in an extreme case, if the background mantle viscosity is basically very small, like water, you can never have water to push very dense rocks up to very high topography, right? Because it's just too soft. You really need some very stronger material to push something up. Otherwise, if you are just too soft, you're just going to have no effects on the very stronger object.
May I ask another question? Because as you say, the generation or the genesis model, typical model is the chemical and thermochemical pairs. Is there any differences between these two LLVPs for the temperature?
Sorry, could you say that question again?
I mean, is there any evidence for the temperature differences between these two LLVPs? Because
conventional, then yeah, there are some evidence from geochemistry. I do not have the figure here, but one person, Li Zhengxiang from Australia, and his collaborator, they published paper in Nature Communication recently, like 2000, just before our paper being published, and they analyzed the chemistry of hotspots above Pacific LLVP and above African LLVP, and they do find the chemistry in these two hotspots, they are systematically different. Okay, and they also reach a similar conclusion, or actually they suggestion or this implication. They said that the two LLVPs may have different dense composition, and then they will have different density. They are, so to be sure, like they are chemical evidence. That is quite quite encouraging.
But I think Liu Jia's question is also relevant to temperature. It's not just composition alone. So are there any temperature differences between Africa and Pacific?
Temperature difference. I believe temperature will be similar because the temperature of the two LLVP, they are controlled by core temperature. And the core temperature, they are just homogeneous everywhere, and they should have similar temperature.
I know the work by Li Zhengxia, it is a NG paper or something like that. I know that the result shows there were some in the level of isotopic or some trace element. So it means a different formation history or something like that. But that kind of isotopic or some trace element may not be the main factor to say, because when you mention the density, something like that, it is must refer to the main element composition.
That's true. That's true. Okay.
Yeah,
that's true. And they show the trace element composition. By trace element composition tells you is compositionally different. And if something is compositionally different, there is a reason to believe that it may have different density as well, right? It's not very strong evidence, but it kind of support.
Yeah.
It's not very direct evidence. The most direct evidence is like from seismic image. If you can tell the density for the two LLVPs, that is more direct. Geochemistry is like there are lots of caveats for the interpretation of the geochemical observations.
Okay.
Thank you.
Liu from Zhejiang University. So the next question, AA asks another one, is that from the seismic models, those velocity interpretations could be underestimated because smoothing and regulation inversion. So the estimation of your LLVP's height could be affected or not.
That's a very good one. Yes, there are smoothing effects for the tomography model, and however, the result is going to change. And let me point out to the results. Like in this figure, the value of this horizontal average velocity, they may change, like shift to left or right, but the turning point may not change. Turning point is determined by the maximum height of the LLVP. Okay, so I mean the trend of this curve is not going to change, although the magnitude may change because of smoothing effects.
Okay, actually I have a question. I think
yes.
Partly a question, partly a comment. So, to my interpretation, in recent 3-5 years, we've seen one more work. People are trying to say the details of these two LLVPs are different. So they have different composition, likely different. To me, that internal density profiles or density or velocity correlations. So in your model that you put out some denser materials, no matter what it is to begin with, but in the end, I think that is more closer to what is happening in the lower mantle is that there might be density differences, density profiles, or very different density distribution within the two LLVPs, just like including the global tomography work. In the recent years, people trying to propose that these two large low velocity provinces might be comprised of different piles. Maybe one has higher density in the lower part, and then in the upper part it has a slightly neutrally buoyant, or the other way around. So it might become close to different pieces, and that this density distribution might not be homogeneous. So I don't know how you view that from your perspective.
Yes. The density distribution is maybe not homogeneous. That's correct. And I'm talking about like overall density, like maybe near the very top, near the very bottom, the density can be a little bit different, but in the center, kind of the major body should be more or less similar if they, and actually because they are caused by the same condition for each LLVP, there's no reason, and there's internal convection mixing, and in my opinion, the density should be more or less, I mean, the compositional density should be more or less homogeneous.
Okay. So any other questions from our participants? Okay, I think with that, that's the end of our webinar today. So thanks everyone for your participation, and thanks our speaker Mimi for giving a talk. Okay, see you guys next week.
See you. Let me know if you have questions. Send me email. Okay.
Okay. Okay. Mimi, we can take a break, and then could you come back in 5 minutes?
Oh, I need to come back.
Yeah, you and me. Yeah, I could talk with you a little bit.
Oh, sure, of course.